Now, I want to start today. I want to mention one of the problems on the last quiz. It's the one that everybody has the most trouble with. But I also want to start with the first problem on the quiz, which people unintentionally typically have trouble with. On the first problem, and I'm sure most of you probably said correct things. You said, I have a couple of restrictions. Okay, I have these two restrictions, and I'm sure probably everybody got that right. Now, I could write this as y is less than x. I could write this as x is greater than y. It really doesn't matter as long as what I'm saying is correct. So when I ask for the domain, what if I wrote this? Okay. Is this correct? You say, you yell
No,
at me.
it's not.
Why is it not correct?
It doesn't have the and.
And why would that matter? Maybe that's a better question. You're absolutely correct.
I cannot answer that, but I know it's wrong.
All right.
Because if the numbers are negative?
No. It's the inequalities are fine. So the first one would be like.
Is it because they both have to exist simultaneously, like at the same time?
Yes, you're on the right path. But how do you say that? So I like what he said. He said, I don't have the and. Would you agree that the first restriction is this?
Mm-hmm.
The second restriction says the product is greater than 0, which basically means the entire first quadrant, the entire third quadrant. So I'll do that in a, hopefully you can see this. Okay. Now, and or are huge. If you're a computer programmer, I don't have to tell you that. If you've had statistics or discrete math, I don't have to tell you that. The and or is huge. And is very exclusive. If any part of an and isn't true, then the whole and isn't true. Or is very inclusive. If any part of an or is true, then the entire or is true. Comma means or. And you say, well, what's the difference? Or would be this half of the plane, or the first quadrant, or the third quadrant. So technically, what does that mean? These three quadrants in their entirety. If I have an or, it would be all three quadrants because I've shaded some part of all three quadrants. But if I say and, then it's got to be the part that they share, which would only be, let's see.
The first and the third quadrant?
Well, actually, half, because remember, it was everything below this guy here, and it was everything. Like, yeah, can you all see this? Now that's a huge difference, isn't it? These two regions here versus all of this. Now, it might seem like a subtle thing, but the difference between and or is actually quite huge. And here's the thing: it's not even that you didn't even know that you didn't have it right. It's that comma in this context always means or. Whenever I say, what are my possible solutions? X is 3 or 5 or 7, we just put commas. But if I said it has to be this situation and it has to be this situation, I can't use a comma because that implies or. I have to actually use the word and. So this is not life and death, but it does actually make a difference whether I say and or. And not saying and means it is an or, because a comma, the default is the or. So that one, that's a minor one, but I want to make sure we all get that one in general. Now, most of this you probably found fairly routine, and limits are something that you haven't done in a while, but the factor and cancel kind are usually pretty easy. The hardest limits are always the ones that are iffy. In Calc 1, okay, Calc 1 just had a test today, and they had a question of this nature. The limit as x goes to 1 of, I'll keep it simple, 1, something like that. Now, undefined is not an answer to a limit question, because you can't divide by 0 in the first place, and you're not asking what's happening at 1, you're asking what's happening on approach. Now, you never have to draw a picture to answer a limit question, but sometimes a picture helps illustrate what the heck you're trying to say. So if I drew a picture of what this looks like, I have a vertical asymptote at x equals 1, and then the graph would look something like this. Okay, it's not that exciting. It's a hyperbola rotated 45 degrees. But because I asked the limit as x approaches 1 and there's a discontinuity in the middle, I have to do the one-sided limits. So in this case, we'd say the limit as x approaches 1 from the left of 1 over x minus 1. We'd say, what's the limit as x approaches 1 from the right of 1 over x minus 1? And then we have to look at behavior because you can't calculate a limit in this nature. So you'd say, well, my numerator is always 1. My denominator is always approaching 0, but from which side? Oh, if I'm approaching 1 from numbers smaller than 1, then x minus 1 is always negative. So I'm approaching 0 from the left. And that is how I determine my answer. I have something that is growing without bound, but always negative. That means this limit is negative infinity. There's no work in between. There's no calculation. And then graphically, I see that. Again, I don't need a picture to verify that, but the picture does help me understand it. This side, we'd say, this is approaching 1, but I'm approaching 1 from the right, which means I'm always going to be positive. So I'm approaching 0 through positive means. So this grows without bound positively. Without the picture, I can make my conclusion. Anybody, what's the conclusion?
The limit does not exist.
Does not exist. And the reason it does not exist, that's the part that we have to remember. It's not the D and E more than why is it D and E? Because the limit from the left and the limit from the right are not the same. That's Calc 1. We get D and E's when the two one-sided limits are not the same. Okay, so this is D and E. What if I had only asked you a one-sided limit? What if I had only asked you this or this? Then the limits would have existed. And in Calc 1, we know that a one-sided limit always exists unless I'm outside the domain. So what do you mean you're outside the domain? That's rare. But if I asked you something like this, let's consider the square root function. Well, the square root function is only defined for non-negative values. It's only defined from 0 to infinity. So if I asked you to approach 0 from the left, there isn't anything from the left. That's not even part of the domain. The domain starts at 0. So this would be a DNE. That's about the only time you're ever going to see a one-sided limit be a DNE, is something like that. That's exceptional. That's not the rule, right? These are more like the standard. So a one-sided limit is going to exist, but in Calc 1, a DNE is going to come when the limit from the left and the limit from the right are different. But a more general way of saying that, if I can approach the value in question from different paths and get different results. Now, in Calc 1, there are only two paths, left and right. But in our class, there's an infinite number of paths to a point, to an ordered pair. Every which way I can approach it on the XY plane is considered a path. So coming up with a DNE in 3 dimensions is actually much, much trickier, because part of the process is how do I even know when I should attack it in that way? So we did a problem on the quiz, and the one on the quiz is just like the one I did in class. It's just like the one in the notes. You know, so we did one of this nature. Sorry. What was x cubed plus y cubed over x cubed minus y cubed. Now, the previous problem that I asked was a quotient of polynomials in x and y, and you got an indeterminate form of 0 over 0. And so you said, let me see if I can factor and cancel. Well, this is almost an identical problem. As x and y both approach 0, my numerator is approaching 0, my denominator is approaching 0. And calculus has taught us whenever you have a rational function, a quotient of polynomials, that is approaching 0 over 0, you're looking for a factor and cancel kind of situation. The problem here is, I don't think I can factor and cancel. I don't think I can come up with something that I can cancel. That doesn't mean the problem can't be answered, but that's a strong hint. That's a strong hint. I can't get rid of the problem child, the thing that's causing me issues. In the previous problem on the quiz, you could factor and cancel something that was causing problems. So it's sort of that saying that, maybe this one doesn't exist, but how do I show it? Because if I try to come up with multiple paths and I get the same limit, that doesn't prove anything, by the way. But it's kind of making me think that maybe the limit does exist. So if I chose different paths, and I'll give you an example. If I said, consider all graphs that pass through the origin, see if x and y are both 0, where n is any number, let's just say n is greater than or equal to 1. Okay, I don't want to do square roots and weird things. I don't want to do things that might have discontinuities. But if I just said, think of n as being an integer. So, lines, parabolas, cubics, everything under the sun. What if I said, consider all paths? So on the XY plane, that would be that. It would be all lines through the origin, clearly, right? All parabolas through the origin from every which way. Oh, that's terrible. All cubics, all fourth. There's an infinite number of different things that can have this. If I said, let's choose this, then I'm going to write it like this, along the path. Because we can get in trouble sometimes. So I'm going to say as x comma kx to the n, along the path y equals kx to the n is going to be greater than or equal to 1. And again, because I don't want to run the risk of certain types of discontinuities. So then on top, I would have x cubed plus kx to the n cubed over x cubed minus kx to the n cubed. Now I can clearly pull an x cubed out of every term. So let me go ahead and expand this first. Oh, 0, 0. Now, if x is approaching 0, you will notice that kx to the n will also be approaching 0 because x is approaching 0. So this would be the equivalent of me just saying x is approaching 0 because now I only have the one variable of x cubed plus k cubed x to the 3n, k cubed minus, x cubed minus k cubed x to the 3n. I can factor and cancel, or to make it easier, I can just multiply top and bottom. That's faster. So the next thing should be the last thing. So I have the limit as x approaches 0 of 1 plus k cubed x to the 3n minus 3. This is part of the reason I said I need x to be greater than or equal to 1, because I need that exponent to be non-negative. Remember, we're going to have x be approaching 0. If I have a negative exponent, then again, I can get, or a 0, I can get into trouble. So I can't have a negative exponent if x is going to 0. That's the problem. That's a minus. Now, I said this one could give us issues. Now, if I allow x to approach 0, both of these terms are going to approach 0, aren't they? And my limit will be 1. Is that a good thing or a bad thing? Well, I just approached the origin through an infinite number of different types of curves, lines, parabolas, cubics, everything under the sun, and I got a limit of 1. That kind of makes me think that the limit might actually be 1. By the way, I have people do this and say, and of course the limit's infinite, or the limit doesn't exist. No, if you get a constant, you can't have infinite. If you get a constant, you can't have a DNE. A constant is a constant. But, and I did a problem like this last day. Here's the key. Because these guys are the same degree, if I make my path potentially different degrees, I usually will get a constant answer. What I really need to do, and this, by the way, this is not in the textbooks. This is something you find through experience. I need a path so that my results after I plug it in will be same degree. I'll give you an example. If this had been x to the 6th and y to the 3rd, I would want my path to be along parabolas because then I would have the same degree. Oh, if this were x to the 9th and this were y to the 3rd, I'd want my path to be along all cubics. That way I can get rid of the x's in the denominator. But because these are the same degree, what I really want is not this path. I want that path, just kx. Why just kx? Because then I'm guaranteed that I can factor and cancel. So now look at the difference, what this does to the problem when I do this. And this is a big change. When I do this, see, the previous one had a lot more paths. There's an infinite number of paths of an infinite number of types of curves. There's infinity for each of one of the infinite things. Yikes! Like infinity squared different paths, and all of them produced a limit of 1, except, oops, if I factor and cancel here, I'm going to have 1 plus k cubed over 1 minus k cubed. And why is that important? Because that limit is 1 plus k cubed over 1 minus k cubed. Great. I just took an infinite number of different lines that pass through the origin. And when I took the limit, I got this thing here, which sure looks to me like it's a constant. So once again, it appears that our limit is a constant. But wait a minute. If I consider every possible line through the origin, then k is nothing more than slope, isn't it? And for every possible slope, this is the problem we did in class, if you remember. For every different slope, won't this give me a different value? If k is 2, I get a different value than if k is 3, or if k is 10, or if k is -7. Oh, so at this point here, I would say something like this. Every value of k gives a different limit. In the previous example, I got a limit of 1 because all the terms that had k's in them would have gone to 0. But now, because I was more judicious in my choice of paths, every value of k gives a different limit. Therefore, just saying words, the limit does not exist because multiple paths gave me multiple results. I never got an infinity. I never got anything weird. I got a constant, but it's a different constant for each value of k. That's how we get a DNE in this case. In the previous one, now there's a tendency people will try to do a DNE for all problems, even ones that aren't. If the limit exists, you can't get DNE. But if it's a DNE, you can actually get a finite limit if you're not careful with your path. We just did that a moment ago. So that's why I say this is generally considered the trickiest problem. All right, now let's move on to today's stuff. So we're going to review a little bit of Calc 1, first of all. Okay. In Calc 1, one of my favorite applications early on, and this is actually the second application we do in Calc 1. It's going to be my lecture on Thursday in Calc 1, to be quite honest. It's what's called tangent line estimations. Okay, so think of the following. Okay, you're back in a time when maybe calculators weren't even invented, or they weren't very good, or you just simply, they were too expensive. Yeah, there was a time they were really expensive. And maybe you just don't have the ability to do a calculation, not easily. So the question was something like this. All right, to the best of your ability, I want you to estimate, how about 4.02, to the 5th power. Now let's have some fun. I don't need to estimate that. I can do that by hand. I just multiply 4.02 times 4.02, and then I do it again, and then I do it again, and then I do it again. I'd fill up a few pieces of paper, and I'd have a really big, ugly, nasty, long, yikes. Not very practical. And especially, what if it wasn't something that was even a rational number? What if it was an irrational number? So the idea of a tangent line estimation, if I considered the graph of y equals x to the 5th power, I know it's going to go up really fast. It's going to go down this way. So let's say, hypothetically, don't worry about scale. Here's the point 4, 4 to the 5th. Okay. I'm looking for the point that's really close to it, right about here. That point right there is 4.02, 4.02 to the 5th power. But what if instead I said, let's draw the tangent line to the point that I know? Then the value on the tangent line for an x value of 4.02 wouldn't be terribly far away from the value on the curve when x is 4.02. So if I drew a picture, I'm going to blow up that part right there hugely. So what I've got is, I've got a curve that's going like this, and I've got a tangent line that's going like this. Okay, let's just kind of pretend. And let's say that point right there, that's 4, and I'll write it this way, 4, f of 4. We have to figure out what f of 4 is. Okay, and then I've got that point there, and I've got that point there. This point here is 4.02, f of 4.02. That's the point that I'd like. But I really don't have the ability to calculate that. And if you say, well, no, I can do it longhand, then I'll make it 4.0002 to the 27th power. We'll make it something that no human being would actually think of sitting there and doing by hand. But if I use the value on the tangent line to estimate the value on the curve, they're not going to be that far apart because I haven't moved that far yet. So what we do is, I'm going to make you a little triangle here. So I make a little triangle. Yeah, this is going to be a little bit tricky. Okay. This is the actual change in X. This is the actual change in Y. Okay. I'm starting at this point, I'm ending at this point. If that's on the curve, delta X and delta Y refer to the changes on the curve. Now let's just look at the change on the tangent line. What we generally do is we use different notation. It's called differential notation. And this is the one rare time we're treating dx and dy as actual physical values. We're not talking dy dx, the derivative. That's not a quotient, that's a thing. I'm talking dx, I'm calling an actual value. Dx is the change on the tangent line, but which is the same, by the way, as the change on the curve for the x value. But right here, that's the change on the tangent line. That part is called the dy. And with differentials, what we're going to do is we're going to use dy to estimate delta y. I don't need to estimate delta x because on the tangent line and on the curve, the change in x is exactly the same. This is always true for the independent variable. The independent variables change on the curve and the independent variables change on the tangent line are always the same. The dependent variable, the change on the curve and the tangent line are not the same. That's why you're doing an estimation. And the symbol you use for estimation, this is where a squiggles comes in. We normally think of squiggles as being asymptotic. That's what it means. Well, it's the same idea. This is a tangent line. If I keep moving this way, it'll eventually become here. I'm using this behavior kind of like almost like a horizontal, or excuse me, a diagonal asymptote. So let me erase this part here. So here's how it's going to look. F of 4 plus 0.02. That's how I want to think about this, where I'm going to say let f of x be x to the 5th power. And our starting point, we'll call it x naught, is going to be 4. Now the starting point has to be something that's easy to work with. 4.02 is not easy to work with. 4 is very easy to work with. That's the place where I started here. I want to estimate this. So this is our starting point. What is our delta x or dx in this case? Well, it would be 0.02. That's how much I moved from 4 to get to 4.02. So this is the part that I want to estimate. I'm going to put EST. Estimate this. And the way we're going to estimate it, I'm going to erase this now. And this is what you did in Calc 1, I hope. This quantity is equal to f of 4 plus the actual change in y. Okay, so I went from 4 comma f of 4. I moved up delta y. That's exactly where I am on the curve. Problem is I don't know what that value is. So I'm going to estimate this with f of 4 plus dy. Okay, and as we know, this one is easy to figure out. The equation of this tangent line, think point slope formula. Okay, point slope formula, if you remember, because I want the equation of the tangent line. The point slope formula is y minus the y coordinate, which in this case, remember, we're going through this point. So it would be boom equals slope. What would slope be? Actually, let me write this as f of 4. That's easier. What's the slope of the tangent line? Oh, it's the derivative of the function evaluated at 4 times the change in the x coordinates. So when I move along my tangent line to this new place at 4.02, This is the dy. This is the dx. That's exactly what dx is. Because I get 4.02 minus 4. Oh, I'd be at my new y coordinate on the tangent line minus this. That's dy. So when I say what's dy, it's simply this quantity right here. So this part here becomes f of 4 plus f prime of 4 dx. Now, these are all just simple values that I can calculate. I mean, they're not complicated values. So let's see. What is f prime of 4? Or excuse me, f prime of x? F prime of x is 5x to the 4th. So what's f of 4? That'd be 4 to the 5th power, so that'd be 1024. What's f prime of 4? Well, that'd be 5 times 4 to the 4th, 5 times 256, so that'd be 1280. So that means for this problem right here, I'm going to use the values, what did I say, 1024 plus 1280 times 0.02. And if I get out my handy dandy calculator, 1024 plus 1280 times 0.02, I get 1049.6. Now, does that mean that that's the value of 4.02 to the 5th power? No, that means that's our estimation of 4.02 to the 5th power. Let me erase this part. So when all is said and done, okay, this was f of 4.02 is equal to this is estimated by this. So in the end, I can say 4.02 to the 5th power can be estimated by this quantity right here. So there's my final answer. Now, we're going to cheat a little bit. You see, when these were first taught a few hundred years ago, things like this, well, they were still a few hundred years away from being invented. I'm pretty sure that I did everything right. I'm pretty sure. Well, can I be more certain? Yeah. Let's actually calculate that and compare it to our estimation. They should be really close if I did it right. They can't, by the way, it would be absolutely impossible for them to be equal because the tangent line escaped the curve. And in fact, in my picture, my tangent line was below the curve. So that tells me my estimation should be a little less than the calculated value. So let's do the calculated value. 4.02 raised to the 5th power. Okay. And I get this is exactly this part right here, 1049.8572832. I feel like I'm a few decimal places short on that one. No, that's what my calculator says. Okay, this is the actual value. This is my estimation. Is that pretty good? Well, but they're not the same. They differ by, 0.25. They differ by 0.25 when the calculation is over 1,000. That means they differ by a really, really small amount. Okay, we're going to talk about what that means, that relative size thing. So that's actually a really good estimation. And this process would be a heck of a lot easier than sitting there and trying to multiply that out. So now, is there a general rule that I can apply to problems? Yes. And it looks like this, okay? Okay, suppose f of x0 is easy. Let's just start with that. That's because we call x0 our happy value. That's the term I like to use, mathematical term. It's our happy value. In this case, 4 was our happy value. 4.02 was not. So to estimate f of x0 plus delta x, or you could say x0 plus dx, this is estimated by f of x0 plus Well, actually, let me write what it's equal first. Sorry. It's equal to f of x 0 plus the actual change, and that's estimated by f of x 0 plus dy, which is f of x 0 plus f prime of x 0 dx. That's the formula. That's what you did in Calc 1, and it's very, very simple formula to use. But what we want to do is now extend that into 3 dimensions and see how does it work when you have multiple independent variables. Okay, so let's start with that. So what if? Now I just want to give you sort of the general. So now, similarly, let's suppose f of x0 comma y0 is easy to find. Now I have a function of 2 variables. Now I'm now in 3 dimensions. This would be the z value. So what I have some surface. Okay, I'm above the xy plane. I'm going to go to my happy point on the xy plane and then project straight upwards. So I'm at the ordered pair x naught comma y naught, and then I go up to the z value, and that one's really easy to find. That's really friendly. Now I want to move a little bit. Okay. I want to estimate f of x naught plus delta x, y naught plus delta y. I want to move just a little bit, and it's understood that delta x and delta y are probably small, because if they were large, in the last example we did, we estimated 4.02 raised to the 5th. But if I wanted to use 4 as my happy number, it wouldn't be very useful if I was trying to estimate 27 raised to the 5th power, starting with 4. No, that wouldn't work. I need to take a value really close to 4. So I need values really close to this. So we assume that these numbers are small. So this is going to equal the point in question. I'm up on the z-axis, but now I've got to move a little bit in the z direction. So I'm going to put plus delta z. Okay, that's going to serve to what delta y did in the previous case. And this will be estimated by f of x0, y0 plus the differential, the dz. And again, that has the same rule as dy did in the last example. But now what will that be? Actually, I'm going to write this on the line below. I'm sorry. But this is going to be this. Now, what is this going to be? Well, in the last example, it was just derivative times differential. It was just f prime of x naught times differential. So this is going to be a derivative. But which derivative? Oh, this will be the partial of f with respect to x evaluated at x naught, y naught. In the previous one, it was f prime of x naught because I only have the one function f and I only had the one value. Now it's the partial with respect to x evaluated at happy point times the change in x. And if I was in 2 dimensions, that's exactly f prime of x naught dx. But now I got to do the same thing in the y direction. So I have this piece and it looks exactly like this piece. So I have the derivative evaluated at happy point times the incremental change. Derivative evaluated at happy point times incremental change. One in the x direction, one in the y. And it turns out if I have 3, 4, 27 independent variables, I just do one of these for each one. It's beautiful. This is, by the way, this is the precursor for next time when we look at how to come up with what's called a tangent plane. Tangent planes in 3D are kind of like what tangent lines are in 2 dimensions. So this is our estimation. And we're going to do a couple of examples because it's just not very hard. All right, so let me just go ahead and start with a function, make it easier. Okay, so let's say that f of xy we're going to define as 3x squared y plus 2xy cubed. How's that? We want to estimate how about f of 2.03 comma 0.98. So it would be equivalent to me putting a 2.03 in for x and a 0.98 in for y. That's all I'm doing. And I don't have a calculator. Yeah, so we're going to do an estimation, and then at the end, we'll check the numerical value to see just, how close are we? So what sort of things do I need to do? Well, first of all, anybody want to guess what's our happy point? What should we choose as our happy point? Because that's really important. Yellow, what do you think? What ordered pair should be our happy point?
2, 1.
Why 2, 1? Because you're right. Why 2, 1?
The closest to those.
Yeah. By the way, having said that, it's the closest. Some people will make the mistake of choosing 2, 0. Ooh, but 0 is very far from 0.98. 1 is very close to 0.98. So 2, 1 is the closest ordered pair that has integer values. That's the only logical choice, but it's easy to see why somebody might choose something different. So we will choose 2, 1 as the happy point. Yeah, it's my mathematical term. You have to start at some place that's easy to evaluate, because remember, where's happy point showing up in your final answer? Showing up here, here, and here. That has to be something that's easy to calculate. Or think of it another way, it's something that has to be easy to calculate without actually using any technology at all. That should be something we wouldn't struggle at. So now the next thing I need to do is take my partial derivatives. And I can do them right here. So whether you write it this way, partial of f with respect to x, or you write it as f little x, it's the same thing. So I like f little x because it's just less writing. That's all. So what's the partial with respect to x? So this is where we get to practice what we learned last day. Partial with respect to x, it's going to be 6xy plus 2y cubed. Okay, everybody got that? Now, what about the partial with respect to y? The partial with respect to y will be 3x squared plus 6xy squared. Do a quick check. Remember, you're holding the other variable as a constant. So I'm only differentiating the y and the y cubed. The x parts just simply act as coefficients. So I have that. Now what do I do? You're not going to use those in function form. You're actually going to find the values, kind of like when you did f prime of 4 in the last problem. So now what we want to do, I need fx evaluated at happy point, 2, 1, and I need fy evaluated at happy point. This is a function, this is a scalar. Don't say this equals constant. No, you take your derivative and I'll evaluate your derivative. So I'm going to evaluate this at 2, 1. So it'd be 6 times 2 times 1, which is 12. 2 times 1 cubed, that's 2. So that value is 14. Okay. 2, 1. So 3 times 2 squared, that's 12. 6 times 2 times 1 squared, that's also 12. So that's 24. I'm almost done. Now there is one more piece. So, well, actually there's 2 more pieces. We just figured out this, and we just figured out this. So actually there's 3 more things we have to calculate. We have to calculate this, and this, and this. So let's start with these guys because they're easier. Looking at that. Now this shouldn't be tricky, but sometimes it makes itself tricky. What is dx? This should be easy. What's dx, everybody? It's not like I got a whole lot of choices.
103.
Why 0.03? You're right, but why? Why isn't it negative 0.03? In other words, why 0.03?
Because you're moving positively along the x-axis.
Okay, I like that. And Sam, I'm going to keep with you. What's dy then?
It's negative 0.02.
Negative 0.02. And does everyone see that's where we're going to make our mistake? The easiest way to think about it, this is my starting point. What do I have to add to the x coordinate to get to here? What do I have to add to the y coordinate to get to here? So that's why that's negative. If I get those backwards, I have done a different problem. I will, not only will I get a different result, that's true, but I will have done a completely different problem. Okay, it wouldn't be these 2 numbers. So I got that. And then the last piece of the puzzle is, what is, I'll do it over here. What is f of 2, 1. I'm going to put a 2, 1 into the original problem. So 3 times 2 squared times 1, that's 12. 2 times 2 times 1 cubed, that's 4. So it looks like that's 16. So we have done everything. All I have to do now is combine the numbers. And this should be fairly simple, but we want to say it in the correct form. We're not saying that my estimation is equal to the answer. It's an estimation. So I want to make sure I get the notation correct. So now f of 2.03 comma 1.98, which equals f of 2 comma 1 plus the actual change in z, is being estimated by what? I'm just going to go right straight to my estimation. Where is it? So 16 plus 14 times 0.03 plus 24 times negative 0.02. Now let's calculate that. So 16 plus 14 times 0.03. And I got 15.94. Okay, so do I say, now I haven't finished. At some point, be bold and make a declaration. Do I write equals this? No, that would be impossible. In fact, if nothing else, I'm inserting 2 decimal place numbers. My answer is 8 decimal places long. This is only a 2 decimal place answer. They can't be equal. It's not an approximation. I didn't calculate it and round it off. No, this is estimated, squiggles. But I didn't need any form of technology. Heck, I didn't need a calculator to do any part of this. Cool. So now, because there's always a possibility we made a mistake along the way. Might have been just an arithmetic mistake, but we may have made a mistake. So here's our check. And you never have to show this. But you should always do this. Otherwise, you're saying, I did all this work. I hope I'm right. No, I want to know that I'm right. I'm going to actually calculate this. I cannot get this, but I ought to get a number that's really close. Why do I know it's going to be really close? Because these numbers are really small compared to everything else. That's why I expect it to be really close. So I'm going to go ahead and insert it right now. So 3 times.
Professor, I think I just missed something, but why is it function 2.03 of 1.98?
Oh shoot, did I do? Oh, but hold on. It isn't. I just can't read my own writing. Let me do this again then, folks, because I don't. Ooh, I may have accidentally used 1.98. Yeah. Ooh.
The one up top too. Yep. Mm-hmm.
Let me do that again. Well, I'm glad you caught it now rather than later. Okay, I'm the only one that can't see this. Okay, let's try that again. 3 times 2.03 squared times 0.98. Make sure I got it right this. Okay. Plus 2 times 2.03 cubed. Okay, that is the right number. Because this was this. I just entered that wrong. So now I just entered this onto my calculator. Yeah, good call though, because that would have been. So the 1598 is my estimation. So here's what I like to do. Right underneath this, I'm going to write the actual calculation. The actual calculation is 15.936685552. 1, 2, 3, 4, 5, 6, 7, 8. How do I know that's the answer? Well, this is something you guys learned as little kids, but probably forgot. If I take a decimal value and I raise it to a power, that tells you exactly how many decimal places it is. A 2 decimal value raised to the 3rd power is going to be 6 decimal places. But because I have 2 of them, that means this is 8 decimals, this is 6. My answer, this is exactly right. This isn't rounded. Now, would you say that's a pretty good estimation? I'd say it's a ridiculously good estimation. Right? They don't even differ until the 2nd decimal place. That's really good. They can't be equal because remember the separation. But the nice thing is I don't have to know what this physically looks like in order to do this problem. This is always wise. You don't have to show this, but this is always wise to do because if these are relatively close. Tell me does anybody know what's the biggest possible error I could make? I shouldn't say the biggest error. What's the most likely error, the most common error I could make? I meant biggest by commonality. We already did. I know Sam knows the answer. Putting you on the spot, Sam. What's the most likely error we make in this problem?
You don't use the minus 0.02.
Yeah, and then I would have gotten an answer that was, this answer here would have been bigger, right? It would have been bigger than 16 for one thing. It would have been too big.
It was
Okay?
like you would be estimating 2.03 and then 1.02, right?
That's exactly that's what I was referring to earlier. If I get the differentials wrong, I'm actually doing a different problem. And by the way, that would be the problem I'd be doing. That's why you got to check this. Now, here's the tricky part. What if this answer was, 15.6 or 16.2? Those aren't radically different. So it's, if you make tiny errors, it's sometimes really hard to catch them. But what if this is 257? Yeah, I think an extreme answer is probably easier to tell that you did it wrong than a really small error. But nonetheless, the fact that these are so close fills me with great confidence. Now, why do we do this? I mean, we have calculators. Why would we go to all this trouble? Well, actually, we go to all this trouble for something completely different, for measurements. Now, let me go back to Calc 1 for a moment, because there's something we did in Calc 1. And again, I doubt anybody remembers the details, because the fact that I'm doing this in my next Calc 1 lecture, and we're only in week 6, you got to go back 2 semesters to the same point. It's quite literally go a year back since you did this kind of stuff. Okay, here's what we do. Okay, we make cubes. Cubes are us, I guess. We make cubes. We make everything from little sugar cubes to those pods that you put out in your driveway that stay there for like the next 10 years, that you intended to move, but you never did. You guys know what I'm talking about. Once you see them in the driveway, they stay there forever. But we make cubes of all sizes. But there can be errors in the dimensions themselves. So I'm going to give you a really simple example, because this is where we're going. This is why you're learning this, is for this part of the application. So let me do a simple example. Okay. Let's say today at the job, Josue on his job, he was off by 10 centimeters on his job. Okay. And Samuel, I'll use Sam because I know he's also on. Samuel on his job today was off by 50 centimeters. So who had a better day? Well,
Fire Samuel.
it kind of depends. Well, Sam is doing this gigantic skyscraper construction, and it's 1,000, let's say it's, I'm sorry, it's 100 meters across, and he was putting the beam down, and the end of the beam was off by 50 centimeters. He's so mad. He was off by 50 centimeters versus 100 meters. That's 0.5%. Josue was performing open heart surgery today, and he was off by 10 centimeters, which is about the size of a human heart. In other words, he killed the patient because, you can't miss the human heart by the size of the human heart. So in other words, Josue's job today as a heart surgeon made a 100% error. Samuel made a 0.5% error. So in other words, it wasn't the size of the error, it's called the relative error. And that's actually the most important thing about error in general. It's never the amount of the error. It's really, think of it more like the percentage of the error. So if I said I'm off by a certain amount, that'd be kind of like this. When someone says to you, oh, I got 87 today on my test. My first thing I say is 87 out of how much? Oh, 87 out of 88, 87 out of 1,000. Doesn't that kind of matter? But if they said 87%, now who cares what it's out of? I now have the relative score. So whether your test was worth 10 points or 10 million points, 87% still tells me exactly how you performed. So relative error, often we use percent in that case, because then it doesn't matter the size, it's only how much is it compared to what it was supposed to be. So relative error is always how much are you off by how much it's supposed to be. That's what it is. So it'd be another example if Trin today on her job, she was off by $5,000. Okay, and Ethan on his job today was off by $5 million. They both do the books. So who had a better day? Well, Quinn has a little flower shop on the corner, and that $5,000 error cost her business. That was just too much. Ethan balances the federal budget. It's measured in tens of trillions. So being off by 5 million, we wouldn't actually know, would we? We're like a 10,000th of a percent. I'm being silly here, but that's the idea. 5 million compared to 10 trillion is nothing. It's absolutely nothing. So relative error, again, it's the size of the error over what it's supposed to be. So when you're doing things, any type of thing you're doing where you're building or construction, there's something called tolerances. Okay, if you've ever worked in a machine shop or any place that builds things, there is what is referred to as acceptable error, because you can't be perfect. If any of you have ever purchased IKEA furniture, that's my favorite example. By the way, I like IKEA furniture. You get the IKEA furniture, of course, you go to put it together, you look at the instructions, there are never any words, they're just pictures. But you got, the holes over here, and you got the things, and they got to fit in, and everything seems to work really well. But do the things that fit in the holes have to fit in absolutely perfect down to the molecular level, or they can be off a little bit, sure. But if they're off by too much, things won't fit. You can't put the piece of furniture together. Your error is beyond the range of what was considered acceptable. The acceptable error is the amount of cushion you have to allow it to still work. If it's off by more than that, then the thing won't work very well, if at all. So there's always an acceptable range of error. Now, I'm not even going to talk about what that is, because it depends on the situation. But if we said, well, the maximum error cannot exceed the following percent, then you have some guidelines. So we make cubes. Okay, we're doing Calc 1. We make cubes, and we know that the volume of this is x cubed. Let's just start with that. All right. And we'll call x, But what we know is, based on experience, that the maximum error in our estimate, we can be off by, we'll call it the edge measurement. That's the most we can possibly, we've found. Now, by the way, we could be perfect. This edge could be perfect. This could be 1% too big, and this could be 1% too small. So whenever we say maximum error is 1%, we mean in either direction. It's not, plus or minus is irrelevant in that case. It's just, I'm off by this much. I liken it to a bullseye. You're throwing darts and you're trying to hit the target. And then I say oh, I was off by an inch. You don't ask, well, but was it an inch too high or an inch too low? Was it an inch to the left or an inch to the right? Who cares? I was off by an inch. The distance from the bullseye to my dart was an inch. The direction I was off is irrelevant. Because if I said, well, I was off by 1 inch too high, then I was off by 1 inch too low, then 1 inch to my left and 1 inch to my right, and then you'd say, then your average is a perfect bullseye. No, my average is to be off by 1 inch. Right? No, I don't get to take my extremes and say, I'll put them right in the middle. No, if I'm off by this much and I'm off by this much, my average is how much am I off in general. Plus or minus does not matter. So in that sense, it's like an absolute value. So if we said the maximum error in the measurement is 1%, then what we're saying is, in a sense, that the maximum error is 1% of what it's supposed to be. So the maximum error in my measurement is 0.1 times what it was supposed to be. And let's say this is true whether it's a sugar cube or whether it's a gigantic pod. 1% still represents the maximum. So what we want to do is we want to find the relative error in volume. Let's call it V. I want to find the relative error in volume. That means that I want delta V over V. Delta V is actually my error in volume. If I'm off by 1% in either direction, delta V is how much my volume is going to be off. I want delta V over V. So whether I'm a sugar cube or a giant pod, I'm going to still say, I'm off by this percent. Okay. So the way it really works is, if I can be off by 1% in either direction, that means I can be 1% too high, I can be 1% too small, I can be everything in between. Now, to make this easier for us to understand in Calc 1, what I do is I say, let me just keep a really simple example. Let's suppose that X is supposed to be 100 centimeters. Then that means the maximum dx would be 1 centimeter. I like to use 100 centimeters, and you don't have to think percent, you can just think actual amounts. So if this is supposed to be 100 centimeters by 100 centimeters by 100 centimeters, a cubic meter, okay, then what's the most my volume can be off? Well, in reality, what you would actually have to do is say, well, let me consider everything between 99 and 101 for each edge. But wait a minute, isn't that an infinite number of values? I mean, if I said every number between 99 and 101, not every integer, every number, there's an infinite number of numbers. So what they used to do is they'd say, okay, no, let's increment by maybe 0.01. So we'll go 99, 99.01, 99.02. Maybe I can go 2, 3, 4 decimal places, and then I'll just increment by that. And I'll calculate every conceivable volume that can be calculated using every range from 99 to 101 for each of these. Do you realize how many calculations that would be? Let's say I went 3 decimal places. That means there'd be 2,000 different values that I would use for each of these. The cube of 2,000 is 8 billion. That would mean there's 8 billion calculations. And what I do is I'd sift through them and find the one that was the largest and the one that was the smallest, and I'd take the relative distances and I'd average them together. That's very, very inefficient. I already know what the biggest and smallest are going to be. The biggest is going to be 101 cubed, the smallest is going to be 99 cubed. But that's only because I have a really simple function. Oh, what if this function was more complicated? What if it had e's and sines and cosines? No, then I would actually have to do the computer generated thing, which, by the way, would be mind-numbingly long. Yeah, it actually would be beyond, really quickly beyond what humans can actually do if I make it crazy enough. So let's consider the high and the low. So if I considered the high, that would be 101 cubed minus 100 cubed. Okay, that would be the most I could be off. Remember, it's because it's 100 cubed. So 101 cubed minus 100 cubed would be 30,301 cubic centimeters. That'd be the most I could be in the high direction. The low would be 99 cubed minus 100 cubed. And that would be negative 29,701. Now, I don't average the positive and the negative because then that would average to almost 0. No. How much am I off? You take the absolute value and average them. So if I said, let me consider the extremes, then the average would be half of 30,301 plus 29,701. And that would give me, what would that be? 30,001. So we'd say then the maximum error I'm going to expect to see would be that much. So the maximum relative error, sorry, it's hard to read, would be 30,001. Remember, it was supposed to be 100 cubed. And that would be 0.03001 or 3.001%. Okay, now I'm doing the easiest shape you could possibly consider in 3D, a cube. It could only get more complicated. And what if I had more variables? What if I had more things in my function? This doesn't work very efficiently. It could get too big too fast. So let's use what we just did, the tangent line estimations, which is also sometimes referred to as differentials. That's what I have it on the syllabus. Let's use that to do this. Let's do the same mathematics we just did with the tangent line a moment ago on this problem right here. This is the actual answer. Now we're going to do an estimation. So all I need to estimate delta V. So we're going to estimate estimate delta V using dV. Well, what would dV be? Well, what was it before? It was the derivative times the dx. The derivative of, oh, what is the derivative of v with respect to x? That would be 3x squared times dx. Okay, so in this case, that would be what? And by the way, that's my estimation of delta v. That would be 3 times 100 squared times 0.01. I'm sorry, sorry. We were using 1. Sorry, right there. And that will be exactly 30,000 cubic centimeters. So delta V over V can be estimated by dV over V, which would be 30,000 over 100 cubed, which is exactly 3%. Remember, the actual value was 3.001%. This is our estimation. I like this better because it's just really simple and really fast. Now, I kind of cheated by giving you specific values just to make the mathematics make more sense when we were actually doing calculations. So here's how you actually would have done this problem if I never gave you any values. I only gave you the 1%. So what does this look like in this case? We write it like this. Sorry, 3x squared dx over x cubed. After I cancel everything, that's going to be 3 times dx over x. Look at that statement right there. If dx equals 0.01 times x, doesn't that mean that dx over x is exactly 0.01? Yeah, if I'm off by as much as 1%, that means that the relative error here is, oh, this is the amount I'm off, this is the amount it's supposed to be. That's what it means to be relative error. So going to that right there, this would be 3 times 0.01. Same 3%. I was going to get 3% regardless of the length of the edge, because that's what the function produced. Now, this is how you found relative error. So hopefully you remember doing stuff like this, but even if you didn't, it's okay, because now we're going to do this in 3 dimensions. So in 3 dimensions, it's a little bit more complicated because I have more variables. So here's what we do. In Calc 1, we made cubes, but cubes are so, well, they're so Calc 1. I mean, there's just one variable. They're so boring. No. We make cans. Let's see. Now we make cans. Why are cans so much cooler? Because cans have 2 independent variables. See, cubes only have 1. Cans have 2. Spheres only have 1. But tin cans, oh yeah. Right, so that's a, it could be tuna, it could be tomato sauce. It's whatever you want it to be. I have a can, but here's the thing. I have radius and I have height that are both independent variables, and both of them can be off, and they can be off completely unrelated to each other. So I could have an error in the radius of a certain percent. I could have an error in the height of a certain percent. So now understand that I would have to calculate these independently, or at least know them independently. So let's say we make cans. We have an assembly plant and we make cans. We make cans of all sizes. But what we found, because our equipment might be old, that we do have some error. Okay, but the amount of error might be small enough that it doesn't matter. So let's say that the relative error in the radius, let's say, is 3%, and the height about 2%. I want to find the maximum. Sorry, I should say the maximum. Sorry, that's kind of implied. The maximum relative error. That to say the maximum relative error means I could be perfect, or I could be off by the most I can be off, or I could be everything in between. Okay, high, low, but we're never off by more than this in any direction. That's what that means. All right, so find the maximum relative error in volume. So what is the volume? Well, this is a circular cylinder, so the volume is pi r squared h. That would be useful to know that. Okay. Volume is a function of two variables. So you can think of volume as actually v of r comma h. That means I'm going to take partial derivatives along the way. And so the easiest way to write this problem out is to do it like this. Delta v over v is going to be estimated by dv over v. But wait a minute, Mr. Brown, you didn't give us any actual measurements. No, I didn't. I gave you the relative errors. You'd rather have the relative error every time. Because if I actually give you the specific measurements, that requires more calculating. If I just give you the relative error, then your final answer is going to be relative error, and it's a lot less calculating. So what am I given? The maximum relative error in the radius is 3%. That means dr at most is 3% of r. By the way, do not say dr is 0.03. That doesn't mean anything. That's a percent. R is a measurement. R is a length. R has units. 3% doesn't have units. No, dr is not 0.03. Dr is 3% of r. That means that dr over r is 0.03. And dr is the measurement of the error. So this isn't an estimation. This is an exact value. Second, I have dh is 0.02 times h, or dh over h is 0.02. I need these two values here because this is going to be the partial derivative of v with respect to r. Now, what's the partial of v with respect to r? I'll write up here. The partial of v with respect to r, that's going to be 2 pi r h. The partial of v with respect to h is going to be just pi r squared. Okay, those are easy. Generally, in any geometric shape, the partial derivatives should be easy because they're not complicated. So with that and with that, I'm ready to answer this question. So it's pi r h dr plus pi r squared dh, right? Partial of v with respect to r dr, partial of v with respect to h dh. And what goes here? What goes here is the actual volume. This guy. Now, what I need to do, there's no calculating to do yet. And by the way, I could substitute things in, but I'll make it easier on myself. Just break up the quotient. So pi's will cancel. One of the r's will cancel. I wrote that correctly. Let's see. And the h will cancel. So pi h, I'm left with a dr and an r. And did I lose it? Oh, I lost the number, didn't I? It should be at 2, shouldn't it? I said 2, but I didn't write the 2. Was that what you're going to say? I read your mind. I'm getting better at that. Yeah, I said the 2, but I didn't write the 2. So this should be 2 pi r. Let's fix that. I hate errors. Okay, 2 pi r. So this should be 2. Now, how about over here? The pi's canceled, the r squareds cancel, and that leaves me dh over h. I haven't really done much. I took a couple of partial derivatives, and when I wrote my quotient, everything canceled so beautifully. How come this is beautiful? Because that's a constant. That's a constant. So this is 2 times, where is it? 0.03 plus 0.02, which is 0.08. Now, how do I interpret that? What does that actually mean? That means the maximum relative error can be estimated 8%. Is it exactly 8%? It's not exactly 8%, but it's going to be, it might be 8.00001 or 7.99999. It's essentially 8%. But I got there without having to take multiple measurements and looking at all the extremes and all that. It was kind of cool. Now, here's why this is so important in the big picture. Most industries do not want to replace equipment or their machines because that is really, really expensive. Let's say we have a bottling plant and we thousands of bottles a month. But we're always a little short, or we're always a little bit too much. It's costing us money. It costs us a lot of money to be off by too much. So the tolerances are the amount we can be off. Those who've had statistics, the study of variance is the most important part of statistics. Another way of thinking of variance is a numerical measure of consistency. When the variance is small, that means you're very consistent. Everything's really close together. If the variance is large, that means you have a great spread. The average might be what you want it to be, but things are all over the map. And the reason that's a big deal is that's far more expensive, right? You have to end up spending much more money to fix things if you have great variance. So variance is basically a measure of consistency. So if you say, I can only be off by a certain amount, you go to the grocery store and you buy the bag of potato chips, and at the bottom it says, 14.6 ounces. And then you open up the bag and you look down in there and you, hello, 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 the great echo, because, it says some settling may occur, but you're looking at that going, I don't think I got as many chips as it says. So you weigh the bag and it weighs a lot less than it says. By law, any business in the United States, by law, if they short you, they have to replace it. If they don't, you report them to the Department of Weights and Measures. They get fined probably more than the business could actually afford to be fined. And a lot of times they will lose their business. But they absolutely, by law, have to replace anything they short you with. You go to a restaurant, you ordered a 16-ounce steak, it comes out 8 ounces. You don't have to pay for that legally, and they have to replace it. Now, you could be nice and say, I will pay for the replacement, but actually you don't have to. If somebody shorts you something, by law, they have to make it right. So if they short you, they've got to replace it. If they're giving you too much, then they're giving it away for free. So they lose both ways. So they want consistency. Now, what's consistent? When you go over to Sprouts and you see the 10-pound bag of potatoes. Now, I don't know about you guys, but I put the 10-pound bag of potatoes on the scale. It's going to be somewhere between probably 9 3/4 and 10 1/4 pounds, but it can't be exactly 10 unless they're willing to slice one of the potatoes to make it exactly 10. So it's going to be a little bit more, a little bit less. I'm looking for the one that's 10 1/4, 10 1/2 pounds. I'm not buying the one that's 9 1/2 pounds. I mean, that would be foolish. So when you're buying things like that, they're going to be all over the map. The average is going to be 10 pounds, but there's not going to be a single bag that's exactly 10 pounds, because that's not how potatoes work. They're not one size fits all. So when we're talking about what's the most we can be off, so your industry might say, oh, our cans, we're only off by a couple percent. So, we can afford to have our can be off as much as, 4% in the volume or 5%. Well, you know what? These really small measurements here produced an 8% error in volume. So my business might say, you know what, that's too much. If I'm shorting people 8%, they're going to notice and they're going to want a replacement. And by the way, I can't resell the original one, so I just ate that. If I'm giving them 8% over, I'm giving them 8 cents on the dollar. I'm losing my entire profit margin in all likelihood. So 8% would probably be overwhelming, but I didn't know it was 8% because those numbers look small. Oh, okay. So that's part of the reason this is extremely valuable, is this is what we actually use in real life to determine how far off something is as a whole. So if I was measuring surface area, totally different animal, because I'd use a different formula and my partial derivatives would look different. But this is kind of a cool application because there's nothing about it that's difficult. I mean, you're going to take a couple of partial derivatives maybe, but that's about it. So we'll go ahead and stop there. If I can get this. Uh-oh. My battery on the mouse is dying. Oh, hey, hold on. This is interesting. I can't stop this. I think our lecture today may just keep going. This is funny. This is a fairly new battery too. Oh dear. All right, folks, we'll just hold on for a second while this continues recording endlessly. I'm going to see if I can find our new batteries, because I don't want to have to. Okay, let me try this. It's got one of those little. Oops, that didn't work. Oops. Sorry, let me try that again. The wrong one. No, it's still not doing it.